It's my pleasure to be able to present this talk on the impact of Professor Rao's research used in solving problems in applied probability. The outline of the talk is basically 4 small sections. Firstly, we're going to look about the research that Professor Rao did on matrix inverses, generalized matrix inverses. Then I'm going to explain how I became exposed to his research, and then a section when I present a variety of results that I've used based on his results. And in the final section, I'll talk a little bit about the formal links that I have with Professor Rao. There were 3 key publications that set the scene for Professor Rao's work on generalized matrix inverses. A paper in 1955 in Sankhya, a paper in 1962 in the Journal of the Royal Statistical Society, and his book on linear statistical inference in 1965. There are 2 other related publications which I've also consulted. His 1966 work in the Festschrift for Professor Jerzy Neyman, and in 1967, a general theory paper in Sankhya on the calculus of generalized inverses of matrices. His paper in 1955 had the concept of a pseudo-inverse, and this appeared in an appendix to his paper when he was looking at the computational aspects of the general theory of least squares. He was looking at solving the normal equations and showed that he could play around with those equations and get an expression that behaved as the inverse of the matrix A that he wanted to effectively invert. In 1962, he was a bit more general and gave a set of conditions so that if ax equals y is a consistent set of linear equations, then x equal to a minus y would be a solution where a was defined as the generalized inverse, or what we'll call a G inverse. And then he showed that if a minus is a G inverse, a minus a equals a, and conversely. And it then found a general solution to those set of linear equations, introducing an arbitrary vector z or z to the last expression there. He also looked at some computational aspects using the sweep out process in solving for generalized inverses. His 1965 paper was a bit more general in that he introduced the 4-conditioned Moore-Penrose inverse, A plus, and he distinguished that from a 1-conditioned G inverse A minus by showing that A plus had to satisfy the 4 conditions that I've labeled there, the well-known 4 conditions of the Moore-Penrose G inverse. And he showed that such an inverse exists and is unique. After he published his book, he actually had in the paper for Professor Neyman necessary and sufficient conditions for a set of equations ax equal y to be consistent, namely that a minus y would be y, where a minus was any G inverse. And then went on to show that necessary and sufficient conditions for a much more general equation, axb equals c, to have a solution was the consistency condition, a minus c, b minus b equal to c, and then gave a general solution, this time involving an arbitrary matrix, Z. And in his paper in 1967, he provided a representation of all generalized inverses from any one. Given a single generalized inverse A minus, then he showed that A minus plus U plus A minus A, U, A minus, where A was a particular G inverse and U was an arbitrary matrix, gave all the G inverses for a matrix A. Then he looked at some necessary and sufficient conditions for a minimum norm solution, and these were effectively the 1-4 conditions for the Moore-Penrose G inverse. And the least square solution of the consistent equation ax equals y effectively required the G inverse to be an A13, or the first and third conditions of the Moore-Penrose generalized inverses. So I was exposed to his research when I was studying for my PhD in 1965 at the University of North Carolina in Chapel Hill. And I was taking a graduate course on the analysis of variance with applications to experimental design. This course was taught by Professor Indra Chakravarti using notes prepared by Raj Chandra Bose. And the term conditional inverse was introduced in this course. And here's just some extracts from Professor Bose's notes, showing that when A was square and non-singular, this conditional inverse was -1. Solution of linear equations. So here's some comments about this. How did Professor Bose and Professor Chakravarti come to know about this work? Well, Professor Bose was from the University of Calcutta, and in 1940, Rao was in the first group of students that he taught. He then became the head of the department at Calcutta and later joined Chapel Hill, UNC, in 1949. Professor Chakravarti did his PhD under the supervision of Professor Rao at ISI in Calcutta in 1958, and he joined Chapel Hill, the University of North Carolina, Chapel Hill in 1964. The three of them, Professor Bose, Professor Chakravarti, and Professor Rao, all edited a monograph published by the University of North Carolina Press in 1969. Now, I was not going to do any research in the general area of statistics, but I was going to do research in applied probability. And here was an opportunity in my coursework to be exposed to various different areas of statistics before deciding on my actual research topic. I had the opportunity to take courses from a number of leading figures in their fields at the time: Professor Norman Johnson, known as Johnson and Cox fame, Professor Vasily Höfting, Professor Walter Smith, whose work in renewal theory, and I actually worked with Professor Smith, he's my supervisor, and Professor Ross Ledbetter, who is quite well known as well. After I finished my PhD, I was engaged in some research in Markov renewal theory and Markov chains. My PhD thesis had been on semi-Markov processes, not directly involving Markov renewal processes, although semi-Markov processes are embedded within such processes. But the first key paper was in 1969 on moments of Markov renewal processes. And that started me going on my work in generalized inverses. In 1982, a paper in linear algebra, a survey article on generalized inverses and their application to applied probability problems. 1988, characterizations of generalized inverses, and then extending that in 1990 to parametric forms. And I'll talk briefly about these four papers. The 69 paper was the first one to identify that Kemeny and Snell's fundamental matrix of Markov chains, which appears in Kemeny and Snell's book in 1950, the Z matrix. I showed that that is a one-condition G inverse of I minus P. Now, this is more general than Markov chains. We're actually looking now at Markov renewal processes. Then the matrix of mean first passage times in such a process, I could find an expression using that generalized inverse Z, and also an expression for the matrix of renewal counts, MT, also involving Z. I'm not going to talk about the other terms there, other than the fact to show that I solved systems of linear equations to get a result using a particular generalized inverse. 1982, in this general survey paper, I showed that if I've got a finite irreducible Markov chain with a transition matrix P, stationary probability vector pi transposed, then if U and T are arbitrary vectors such that U transposed E, that's a vector of ones, that says that the sum of all the elements of the vector U are non-zero, and pi transpose T is non-zero, then I minus P plus T U transpose is non-singular, and that inverse of that matrix is a G inverse of I minus P. And then I showed any G inverse of I minus P has that general form involving an arbitrary vector F and another arbitrary vector G, that general form. I used that extensively in some general procedures for finding stationary distributions, moments of first passage times, asymptotic forms for the moments of occupation, random variables. In particular, I had this general expression by computing a matrix A as I minus P times a generalized inverse G to give an expression for the stationary probability vector, and an expression for the mean first passage time matrix using any generalized inverse, and analogous to the renewal counts, in this case, the expected number of times state J is visited from state I in N trials in a Markov chain has got that expression. I also extended this to Markov renewal processes and Markov chains in continuous time. I then went on to characterize generalized inverses associated with Markovian kernels in terms of the 4 conditions that Rao introduced regarding the Moore-Penrose generalized inverse, and also an additional 5th condition for square matrices requiring AX equal to XA. And then I gave a whole range of characterizations for the 1, 2, the 1, 3, the 1, 4, the 1, 5, any arbitrary collection of those generalized inverses, all including the condition 1, the main condition for a 1 condition generalized inverse. I showed that the group inverse had a nice simple expression in terms of any G inverse, and the Moore-Penrose inverse one could compute. This is the Moore-Penrose of the Markovian kernel I minus P. In the follow-up paper in same paper 1988, I showed that you can express one generalized inverse, this I minus P plus T2 U transposed inverse, in terms of any other generalized inverse where some pre and post multiplying terms are specified and an arbitrary constant involving the limit matrix, which is E times pi transpose. And then showed a nice little subsidiary result that this particular matrix, A delta, doesn't depend on delta. The final paper in those 4 papers was the parametric form, and that was, if you give me any generalized inverse G of I minus P, we can always find parameters A, alpha, beta, and gamma such that G can be expressed as this inverse of I minus P plus alpha beta transposed plus a gamma times E pi transpose. Now recall, alpha is a column vector, beta transpose is a row vector, so that of course is a matrix in there. And then I showed that the alpha and the beta and the gamma can be expressed in terms of the matrix A, the matrix B I've given there, and also the generalized inverse G. And I've got some other relationships, but the nice thing that came out of this was the A12 generalized inverse satisfying conditions 1 and 2 for the Moore-Penrose conditions. The gamma has to be -1. And for A13, alpha has to have a particular form, A1 form, beta has to have a particular form, and A15, which is a unique matrix for Markov chains because I minus P is a square matrix, the alpha is E and the beta is pi. I've summarized and elaborated more on this early material by including it in some books of mine in 1983. It's a typo there, it's not 1883, it's 1983. Mathematical Techniques of Applied Probability, Volume 1 and Volume 2. Volume 1 has now been republished as an ebook by Elsevier. And then I've got 15 other papers here that I've listed where I've used generalized matrix inverses and extended the results to a number of different applied probability areas. I'm not going to go into all of those papers. There's some more papers here and some further additional ones. So you can see that I've used generalized inverses quite extensively in my research, but I'm going to highlight some key results in some of these papers. In 1992, a way of taking any generalized inverse G and finding expressions for the stationary probabilities pi j and computing the mean first passage times mij in terms of the elements of G and the elements of a matrix A, which is I minus P times G. And there's a simple computational process which is easily done using, for example, MATLAB. Then I got into some work on perturbations of Markov chains, where I take the transition matrix P and make a small change to it to create a matrix P tilde, and then you get the difference between the two stationary probability vectors in terms of a matrix H, which is involving any generalized inverse of I minus P. And furthermore, some expressions involving some terms involving the mean first passage times in a matrix N for any general perturbation E. I then went on to look furthermore into this, because trying to work out what the significance, if I go back a slide, go back to this matrix N, the significance of the elements in this matrix N. And it turned out that if I look at the sum j equals 1 to m of mij times pi j, that's sometimes now called the mixing time or the time to stationarity. And in a finite irreducible Markov chain, that's independent of the initial state. All those expressions for each value of I is constant, and it's now known as Kemeny constant. And then I showed that if I take any generalized inverse of I minus P, I can get an expression for eta, or Kemeny constant, in terms of the trace of that generalized inverse. I also showed that for any irreducible Markov, M-state Markov chain, that the Kemeny constant was always greater or equal to m plus 1 on 2. And then an application to perturbations of Markov chains, I was able to get bounds on the difference between the two stationary probability vectors in terms of Kemeny constant. In 2007, a paper in Asia Pacific Journal Operations Research, I have a variety of expressions using different generalized inverses for finding mean first passage times in the stationary distributions. Here is just a simple result, a simple addition of the matrix where adding on a matrix EB transpose. EB transposed is a vector with zeros everywhere but 1 in the bth position. And I just show that one can get simple expressions for the stationary probabilities and the mean first passage times. Then extended some work in 2008 to look at the variance of first passage times and some applications to mixing times in Markov chains. Showed that the second moment of the first passage time distribution can be expressed in terms of any generalized inverse G, and the M, the mean first passage time matrix, and got a vector for the variance of the mixing times. And this matrix, this mixing matrix that you end up with, was what we had before for that matrix N. Looked at some works in Markov chain properties in terms of the column sums of a transition matrix, and defined a new inverse G inverse H involving just a vector of ones and a vector of the row vector of the column sums of the transition matrix, and showed that you can express the the stationary distributions as a linear combination of the Hij, and some relationships within the mean first passage times. And once again, Kemny's constant appears in terms of this matrix H. And the final results I'm going to talk about here are generalized inverses of the Markovian kernel I minus P in terms of properties of the Markov chain. Suppose you're given any generalized inverse of I minus P, then you can find the parameters, the alpha, the beta, and the gamma that we had before. And I can show that the elements of that generalized inverse can all be expressed in terms of the parameters, the mean first passage times, and the stationary probabilities. So that's, I think, a lot of applications of these results. And further, if K is Kemny's constant, I get an expression in terms of the delta J from this expression for delta up here, some of the beta parameter times the mean first passage times MKJ. Now, I've had some opportunities to meet personally with Professor Rao. I was involved in inviting him to New Zealand in 2005. He was the keynote speaker at the International Workshop of Matrices and Statistics held at Massey University in the Albany campus, and I was chair of the local organizing committee. We had organized for him a workshop at the University of Waikato, organized by Professor Naijon. He was the Nokia lecture at IWMS, and that was organized through Simo Puntinen. I had him arranged to be a distinguished visitor to Massey University and also a visiting lecturer for the New Zealand Statistical Association. We worked him hard. He had an extensive program. He visited every university in New Zealand, gave public lectures, and spoke at our workshop, as well as this data scrutiny and data mining workshop at Waikato, Ruakura. And here's an advertising blurb for the International Workshop of Matrices and Statistics, where he was figured as a keynote speaker. And here's a photograph of him with Mrs. Rao and members of the organizing committee, Professor George Stein, Professor Joachim Werner, and another invited speaker at the conference, Professor Shale Searle from Cornell, who's now deceased. Professor Searle was a New Zealander. And here is a group meeting, a photo of the group. I can see Simo Puntinen in the middle, in the third row back. Professor Rao, of course, in the front row. Professor Stein in the back row. And there'll be some others probably well known to some of you. I had an opportunity for him to sign my copy of his book on the linear statistical inferences applications, a nice little footnote to his visit. And then he invited me to go and be a keynote speaker at a 2-day workshop at Penn State University, University Park, where he was based. And there were 4 speakers at that meeting, Professor Jean Golub, Professor Tom Kalias, myself, and MB Rao from the University of Cincinnati. And this was the workshop schedule. He had me giving 2 talks. The only Tom Kalias gave a couple, and so did Jean Golub. And C.O. Rao gave his talk on anti-eigenvalues and anti-singular values that he talked on in the conference in New Zealand the year before. And so here was a photo of the 5 of us, Professor Jean Golub, myself, Professor Rao, Professor Tom Kalias, and MB Rao. And then Professor Rao invited me and my wife to visit him in his home at Penn State University Park, and a photo taken in his residence. So some final comments. As an undergraduate in mathematics at the University of Auckland, I was exposed to some of his pioneering classical results, in particular the Cremair-Rao lower bound. And I had the opportunity to meet Professor Cremair, and he wrote a book with Professor Ledbetter. So there's connections that I had there through that Cremair-Rao bound. While the significance of Professor Rao's contributions to a number of statistical fields is well known, I'm proud to have been able to apply his outstanding contributions on generalized inverses and their use in solving systems of linear equations to a large number of problems in applied probability. Thank you.
Okay.
Thank you, Professor Hunter. It's very exciting to know about your intensive academic interaction with Professor Rao, both in Penn State as well as in your own university. It's a very good, extensive presentation. Thanks for keeping us aware of your deep interaction with Professor Rao. Thank you.
My pleasure.
We can